in part C, the difference between A and B and C and D is that in part C and D, we've been given an initial condition. We've been given a point on the f of x or y graph. And because of that, we're going to be able to solve for the plus C. So it's still the same thing. We need to separate and integrate this. So to do this, we need to separate it, we need to have times factors. So I'm going to rearrange this. I'm going to have dy over dx, but I need to factor this. Unless it's factored, I cannot separate the x from the y. So now that it's factored, I can put these y's together. I can put these x's together. So it's going to look like this, dy over y plus 1, and that's going to be equal to x dx. Integrate both sides. So I'm just going to change that to red. Okay, so then I'm going to integrate both sides now. And I end up with log y plus 1. That's going to be equal to x squared over 2. And there is this plus c, but because we have this initial condition of x is 0, y is 0, we can substitute x is 0, y is 0 into this expression now, and we can actually solve for the plus c. So I end up with log, I'm going to end up with log y plus 1. That y value is 0. And that's going to be equal to x squared over 2. So that x value is going to be 0, so I'm going to substitute 0 into there. And then what's left over then is this plus c. So solving this, log of 1 is 0, 0 squared over 2 is 0, so we get c is equal to 0. Once I've done that, I have log y plus 1 is equal to x squared over 2. And now I have a specific solution that passes through the point 0, 0. So solving for y, I'm going to end up with y is equal to e to the x squared over 2, and that plus 1 becomes minus 1 on this side. So this represents the specific solution to that differential equation that passes through that point 0, 0. So in this case here, we're going to do the same thing. We're going to separate our variables. In this case, it's already separable. So we have our y's and dy's can separate. Our x's and dx's can go together. So I'm going to separate that out. dy over cosine squared y, and that's going to be equal to e to the x, and the dx goes on that side. So the integral of e to the x dx is pretty straightforward, but to integrate cos 1 over cos squared y is a little bit complicated because we don't really have a way to anti-differentiate that. So we have to recognize that this is really cos squared in the denominator is really secant squared. And we do have an antiderivative for secant squared. So if we look at our formulas, that is going to be tan. So on the left-hand side, secant squared y dy integrates to tan y. And on the right-hand side, that just becomes e to the x. And don't forget the plus c. Now, again, we can solve for this plus c because we've been given an initial condition of x is 0, y is pi over 3. So we're going to then substitute in tan. The y is pi over 4. And the x is 0. So we end up with e to the 0 plus c. This allows us to solve for the plus c. So tan of pi over 4, so tan of 45 degrees. So I can always just draw this out. So at 45 degrees, the slope is equal to 1. Okay, so this is equal to 1. E to the 0 is 1 plus c. That makes c equal to 0. So now I've solved for c. I end up with tan y equals e to the x. And then solving for y, we undo that tan with an arctan. So we end up with the arctan of e to the x is equal to y. And this represents the specific solution for that differential equation. And this solution passes through the coordinate 0 and pi over 4.